Hi, everybody. It's great to be with you, even if it's only in pre-recorded and remote form. I'm really excited about this workshop, and I'm sure I'm already enjoying myself in real time. So I want to tell you about some work that we've been doing on intuitive physics in my group at DeepMind. And in particular, exploring how far we can get with a learning-based approach. So I want to start by mentioning very saliently that this work that I'm going to describe was conducted primarily by Luis Pallado in sometimes collaboration with Ari Weinstein and Dhruva Tirumala. And I've been involved and had a lot of fun with it, but I just want to make sure to take a moment to really acknowledge that this is really Luis's accomplishment. So let's just start with intuitive physics as a topic. I think in this context with this audience, there's very little to say that won't be obvious, but our interest in intuitive physics from an AI point of view lies in the fact that it's sort of the domain par excellence of common sense reasoning. There have been amazing advances in AI on multiple fronts, including victories over human experts in very complicated video and board games, of course, and navigation tasks. We can get pretty compelling performance there. Language is now a domain in which pretty interesting innovations are occurring. But when it comes to practical action in the physical world and the kind of common sense that's involved in that, I think everybody agrees that there's a long way to go before we can match human intelligence, let alone exceed it. So it's about common sense, but it's also more specifically about intuitive physics, because intuitive physics, of course, is critical to practical action. More generally, it's been proposed that intuitive physics is fundamental to conceptual knowledge in other domains. Many of you will know the literature that I'm referring to, which suggests that our semantic knowledge or conceptual knowledge basically starts with intuitive physics and engagement with the physical world, and then there's a sort of analogical extension to many other domains using schemas like containment and so forth. But there's a third reason that we're interested in intuitive physics, or at least I should say I'm interested in it, which is that to me it's an exemplary compositional domain. We appear to understand the world in a way that involves breaking it up into pieces and then thinking about the relations between those pieces. So if we can understand the way that that happens in the realm of intuitive physics, then maybe we'll have a leg up on understanding how compositional thought and computation occurs in general. So our approach to intuitive physics, as you'll see, is directly inspired by developmental psychology. And it's inspired in two complementary ways. The first has to do with the way that we approach measuring knowledge in this domain. And the other has to do with the actual learning architecture. So to start with the evaluation side, we take from developmental psychology the notion that intuitive physics knowledge can be analyzed into a set of fairly isolable physical concepts. So you can ask whether a system, be that system a child or a deep learning system or some other AI artifact, you can ask whether it understands intuitive physics by probing a set of particular concepts, and I'll enumerate a few of them. Of course, many people in this audience will already know more than me on this front. And then the other idea that we take from developmental psychology is that one good way to probe intuitive physics knowledge is by testing the predictions of a viewer when confronted with a sort of video prefix. What subsequent events does that viewer predict or expect. And the way that we probe these predictions or expectations is by using a particular behavioral experimental paradigm from developmental psychology that's referred to as the violation of expectations paradigm. So we're going to use pairs of probes, one of which will always be physically plausible and one of which will be physically implausible, to probe a set of very specific physical concepts. Again, drawing these very directly from the developmental psychology literature. So obviously this video is looping, but you can see that there's kind of a normal bouncing effect in this video and an abnormal one here. And this particular set of probes goes after a concept that's been referred to as directional inertia, which, you know, hopefully the concept is obvious, and it has to do with the trajectories that objects follow in physical space. So I'll say more about our data set, but I'm just showing you one example of a probe here, and there are, in fact, many procedurally generated versions of these inertia effects, and everything's counterbalanced in a very careful way that I'll say more about in a moment. But there are four other physical concepts that we decided to focus on. One is referred to as continuity, and that's simply the idea that objects tend to follow continuous paths through space. So examples of plausible probes you can see on the left. There's a lot of variety with a moving camera and different geometries and different points of view, but each of these videos involves a ball rolling behind two pillars. And then the physically implausible event would be something like what's depicted on the right here, where the ball fails to appear between the pillars. And I mentioned counterbalancing before. So an example here would be that the probe data set would also include implausible events where the ball appears only between the two pillars and never appears outside of their kind of parenthesis. And having that combination of foils allows us to match our plausible probes against our implausible probes at the frame level. So we anticipate that in a system that gets intuitive physics, we should see greater surprise with the violation of expectation that occurs over on the right. But if we see that, it can't be attributed to differences in at the single frame level. And in fact, we also controlled for transitions between adjacent frames. So there's no difference in statistics between our test time probes for the plausible and implausible events at either the single frame or the single transition level. So in order to be surprised by the physically implausible events, a system would have to actually have richer knowledge. The third concept that we went after, again, drawn directly from the developmental psychology literature, is object persistence. And many of you will recognize these probe videos as being based on the famous Baillargeon drawbridge experiments. So these particular videos have the events occurring very much at the top of the field of view, but you can still hopefully see that there's a block sitting on the ground, and then this plank is falling on top of the block. And of course, the block being a solid object prevents the plank from going all the way down to a flat position. And then the physically implausible event on the right involves the same event, but with the kind of magic trick at the end. And again, things are very carefully counterbalanced so that there are also probes here where there's no block, or there's a block that's actually alongside the trajectory of the plank, and the plank nonetheless stops in a position that it would assume if there were a block beneath it. And it's that kind of counterbalancing that allows us to control and match on the single frame and single transition level. The next phenomenon or concept that we went after has been referred to as solidity. And it's probed by, as you can see in this diagram from a developmental experiment and in our videos, dropping objects inside containers. And if you assume that this container has a bottom and doesn't have sit over a hole in the ground, then that should allow you to predict how these blocks that have different lengths are going to end up posed inside the container. And the implausible events either have the container swallowing up blocks that should stick out the top, or blocks that stop too soon because they're short and they should go all the way to the bottom and out of view. And again, one of my favorite aspects of this data set is this moving camera, which is not just visually cool, but also creates occlusion and de-occlusion in a very rich way. The next phenomenon that we went after has been referred to as unchangeableness, and this is just the simple idea that objects tend to retain their visual properties over time, even under occlusion. And so the basic idea is an occluder goes down, and in a normal world, the objects that get occluded look the same when they're de-occluded, and in the magic trick, they change either their position or their color or shape. Okay, so those are the probes, and again, we're interested in a system that is more surprised by the magic tricks than by the normal events, following the standard developmental psychology violation of expectations paradigm. But equally important is the set of videos that we used for training. So it's really important, of course, for a learning study to use training data that, that involves a satisfying amount of train test separation. So you don't want to train the learning system on videos that look disappointingly similar to the probes that you're going to use in order to test for surprise. And so what you're seeing here are examples of the kinds of training videos that we used, which were procedurally generated using the same assets that are included in the probe events, but there's never an event in these training videos that corresponds to exactly what the system would be probed with at test time. I should just mention in passing that these videos were generated using the Mojoku physics engine. There are 300,000 videos, each of which involves 15 frames. You're just seeing a high-res, high sampling rate version here, but each video included 15 frames and a 64 by 64 resolution. And then each probe category included 5,000 probe videos. So lots of variety, but always describing the same kinds of events, and then also including the kind of counterbalancing that I described. Okay, so that's our data set, and we're getting things lined up so that we can open source that, so people can use it as a resource in their own research. We refer to it as the physical concepts data set. And many of you will know it's kind of a new edition of a data set that we introduced a few years ago. And I'll say more about that in a minute. But let's come back now to the main thread and talk about the learning system. So here again, we decided to take inspiration directly from developmental psychology and build a learning system that includes three key ingredients. The first is predictions. So of course, if we want a system that's surprised by magic tricks and shows these violation of expectation effects, then it has to be making predictions about what comes next in a video. That's sort of a gimme. But then two other ingredients that are that we take on board from developmental psychology are that intuitive physics knowledge rests upon a more fundamental knowledge about the world, which involves the fact that the world is made up of objects, of discrete objects. And so we build a system that has a bias to represent the world in that way. And then second, an insight that's come both from developmental and cognitive psychology, the human visual system doesn't just represent the world in terms of object, but it also tracks objects over time. So there's something like a visual index associated with each object, and the identity of objects is somehow represented over time in a way that allows you to relate an object at one time step to a corresponding object at another time step. So these were the high-level ideas that we wanted to build into our system. Now, fortunately, because we were interested in building in as little privileged information as possible, there do exist deep learning systems that can learn to carve visual data up into discrete objects without supervision. And I'm referring here to a couple of systems that my group has introduced, something called Monet and a related system called Iodine. Without going into the details too much, the Monet, and in fact also Iodine, centers on a variational autoencoder that learns to create vector embeddings of individual objects by learning a masking function that picks out patches in images and uses those to reconstruct images piece by piece. And there's a variational objective that in the end encourages that, that masking function to pick out discrete objects. So you can see it operating on image data from the Clever data set here. In any event, this work's been out there for a while, so I won't say too much more, but we're simply going to assume that there's a learning system involved in this overall physics learner that carves the world up into objects. And we're going to also assume that the system is able to track individual objects over time. And here again, we're fortunate that recent work has indicated how this function could also be learned directly from raw visual data. So if you're interested in this, I refer you to this paper that was just put on arXiv from some of my collaborators at DeepMind, which takes Monet-like objects and learns to track them over time based on an unsupervised or self-supervised loss. So we're just going to assume that those components are available to the system, and we're going to take images from videos and use ground truth masks, sort of pretending, as it were, that they're coming from something like Monet or iodine, and use them to create object embeddings for each frame. And so the encoding of each frame is essentially a kind of a list of object embeddings. We furthermore cache the object embeddings from every step in the video, and we give the current frame information and all of the past frame information as input to a graph net that uses a single set of weights to compute a pairwise function between all objects. And then those pairwise computations are fed into an LSTM recurrent neural network, which operates at the level of individual objects. And the job of the LSTM, based on the objective function, is simply to predict the next frame. So the overall idea is very simple. In a way, what we're building here is an exemplar of what could be a much larger family of prediction systems that simply take on board the notion that the world is represented in terms of objects that are tracked, and that there's relational processing and integration of information over time, and that the whole thing is used to do prediction. We nicknamed the system Plato, which is meant to stand for physics learning through auto-encoding and tracking of objects. Okay, so we're going to train Plato on these free-form, procedurally generated training videos, and then for each physical concept, we're going to present both the physically plausible videos and a set of physically implausible videos, again, with this very exquisite matching across the two. And we're going to look at object-wise pixel loss as an indication of surprise. Okay, so what do we get? So shown in green is our VOE effects from Plato. And you can see across the 5 concepts that we evaluated, Plato is showing robust VOE effects. So on the top, you see the actual measure of relative surprise, which is normalized in kind of uninteresting ways. But in any event, what matters is the error bars. You can see that across 5 seeds, Plato is very consistently showing surprise effects in all 5 categories. And if you instead code the results in terms of accuracy, how often does, for any pair of plausible and implausible, how often does Plato get the answer right in terms of assigning those labels? It does pretty well. It's not its ceiling. One thing I've been wanting to do is some human baselines, because actually these videos are a little tricky in some cases. But in any event, we see these VOE effects. Now, importantly, we don't see those robust results when we look at baseline comparison models that are based on Plato, but that ablate some of the key ingredients. And in particular, shown in light blue are results for a system that has the same number of parameters as Plato, but doesn't use an object-based encoding. Instead, it tries to embed the entire video into a single object embedding. That creates a tight bottleneck compared to Plato. And so in order to make an apples-to-apples comparison, we built another version of Plato, which has a single embedding for an entire image, but the size of that vector is the same as the concatenated object-specific vectors from Plato. So this system has many, many more parameters than Plato, but you can see it's not doing well at all in general across these 5 categories. So there's more to look at. You can look at the time courses of surprise in Plato, and they're sort of reassuringly aligned to the emergence of the physically implausible event. And you can also look at effects of sample complexity. So the data points at the right here are the averages across all 5 conceptual categories with the full physical concepts data set. But then we did additional simulations, or I should say Lewis did additional simulations subsampling that data set and looking at what kind of effects we see with smaller training set sizes. And interestingly, the effects that we get are pretty robust all the way down to 50,000 training videos. So just to give you a sense of how much data this is, the entire physical concepts training set is the equivalent of about 7 days of visual data, continuous presentation across 7 days of clock time. And getting by with 50,000 videos is like presenting only 1.2 days of data. So really rather meager amount of visual training. So conclusions, Plato gives us robust VOE effects. We find with these ablations that object level representation is key, exactly as ideas from developmental psychology would lead us to expect. We can get these VOE effects with refreshingly little visual data. Our interpretation of the object level effect is that that object level representation operates as an effective form of regularization in learning. And one indirect piece of evidence for this, which I didn't mention so far, is that if you train Plato on videos that look more like the probe videos, so you stop worrying about train test separation, you can get VOE effects even without object level representation. It's only when you introduce this very strong train test separation that object level representation turns out to be key. So suggesting that it's operating as a form of regularization. Now, obviously, there's lots to say about related work, and I don't have time to go into it, about which I feel rather guilty, but maybe we can get into it in discussion. Obviously, there's a lot of work on the effects of including object level representations in general into deep learning systems, including work on question answering and RL. And importantly, there are other violation of expectations data sets, most importantly, the InFIS data set, which came out pretty much at the same time that our original version of the physical concepts data set came out in 2018. And there's lots to say about the interesting relationships between our data set and InFIS. Maybe we can get into it in discussion. But for the moment, I just want to wrap up and say a few closing words on the potential implications, not for AI, but for developmental psychology. And one thing I want to say out loud is that we really don't intend Plato as a serious developmental psychology model. There's all sorts of reasons why it can't be presented as with a straight face as that. But at the same time, we hope that the work that we've done here does carry some useful insights for developmental psychology, including indirect validation for the essential role of objects, something that's already been proposed based on developmental data, and that intuitive physics defined in this way might be learnable to a large degree, at least, from visual data, and not too much visual data, as long as you have the right regularization, and objects are an important part of that. So we think it would be really fun to extend this work to make better contact with developmental psychology, including training it with more naturalistic data. And of course, there are some really interesting data sets that are starting to show up. For example, if you want to check out a cool example, I've included a link here from Linda Smith's lab. And then, of course, you can look at more developmental relevant phenomena like order of acquisition effects, the sort of thing, for example, that Jay McClellan has done, I'm referring to a paper here with Anna Shapiro on the balance beam, the balance scale effect, classic work in developmental connectionist modeling. So there's an opportunity to take things in that direction. So that's my time, but I just want to wrap up by again acknowledging the people who really did this work, and in particular, Lewis, who really is the force behind all this. And thank you for your attention, and I will look forward to discussing with you. Thanks.